Ever wondered why an ice cube rises while water sinks? ecological is all about hydrogen bonds forming a spacious lattice that keeps ice lighter. When you drop an ice cube into water, it immediately rises, showing that ice is less dense than liquid water. The surprise comes from the fact that most substances become denser when they freeze, but water behaves differently. This difference originates in the way water molecules arrange themselves as they cool towards 0°C. Each molecule can form up to 4 hydrogen bonds with its neighbors, creating a tetrahedral network. In this network, neighboring molecules are held farther apart than in the disordered liquid state. The result is an open lattice that occupies more space per molecule, increasing the overall volume of ice. Because mass stays roughly constant while volume grows, the density of ice drops to about 0.92 g/cm3. A lower density means ice experiences a buoyant force larger than its weight, so it floats on water. This property is crucial for aquatic life, as it insulates bodies of water and prevents them from freezing solid. It also explains why frozen lakes have an insulating layer that protects fish during winter months. Thus, the unique hydrogen-bonded structure of ice makes it lighter than liquid water. 0.8. A water molecule consists of one oxygen atom bonded to 2 hydrogen atoms, forming a bent shape with an internal angle near 104.5 degrees. The oxygen atom carries a partial negative charge while each hydrogen holds a partial positive charge, creating a permanent dipole moment. When 2 water molecules approach, the slightly positive hydrogen of one is attracted to the slightly negative oxygen of the other. This attraction is called a hydrogen bond, and it has a preferred direction because the lone pairs on oxygen point toward the hydrogens. In liquid water, molecules form a dynamic network of hydrogen bonds that constantly break and reform, allowing them to pack closely together. When the temperature drops below 0°C, the kinetic energy decreases and the hydrogen-bonded structure reorganizes into a more open lattice. This lattice contains empty spaces that reduce the overall mass per unit volume, making ice less dense than liquid water. Because density is mass divided by volume, a lower mass in the same space translates to a lighter material. Thus, when water freezes, it expands and floats, which has profound ecological consequences for aquatic life. Understanding the molecular geometry and hydrogen bonding pattern explains why ice is lighter than liquid water and how this property supports life on Earth. 0.8. In ordinary ice, each water molecule forms 4 hydrogen bonds with its neighbors. These bonds arrange the molecules in a tetrahedral geometry that is more open than the compact structure of liquid water. The result is a crystal lattice known as ice-eye, which contains regular voids between the tetrahedra. Because space is left unfilled, the mass per unit volume decreases, making ice less dense than liquid water. When water freezes, the hydrogen bonds lock into place and cannot rearrange to fill the gaps that would otherwise reduce volume. The fixed angles of 109.5 degrees between bonds prevent the molecules from packing tightly together. Consequently, each unit cell in the lattice contains more empty space than an equivalent volume of liquid water. This open framework is why a block of ice floats on its liquid counterpart. The phenomenon also explains why glaciers move slowly. The low density allows them to slide over bedrock. In summary, the tetrahedral hydrogen bond network creates an open lattice that reduces overall density compared to liquid water. 0.8. Water Eurostrade's density rises as it cools from room temperature until it reaches a maximum near 4 degrees Celsius. This peak occurs because the hydrogen bonds between molecules become more ordered, allowing them to pack closely together. As the temperature drops further toward 0, those same bonds strengthen and form an open hexagonal lattice that occupies more space. The resulting crystal structure of ice has about 9 circumflex % lower density than liquid water at the same pressure. Consequently, a drop of ice floats on a glass of water, illustrating how temperature controls mass per unit volume. The relationship between density and temperature for water is plotted in a Bella-Euros-shaped curve that peaks at roughly 4 degrees Celsius. On the graph, the left side shows decreasing density with cooling, while the right side shows increasing density as water warms toward its boiling point. The maximum density point represents the most efficient molecular packing before the lattice opens up again at lower temperatures. Understanding this curve explains why lakes freeze from the top down and why icebergs drift in the ocean. It also highlights how small temperature changes can lead to significant volume shifts, a key factor in many natural processes. Pause 0.8. When water freezes, its molecules arrange into an open hexagonal lattice that creates more space between them than in liquid form. This increased spacing reduces the overall mass per unit volume, making ice less dense than liquid water. Because density is lower, ice experiences an upward buoyant force that keeps it afloat on the denser liquid beneath. Floating ice forms a natural insulating layer that slows heat loss from ocean water to the cold atmosphere. This insulation preserves surface temperatures, allowing polar ecosystems to thrive despite harsh winter conditions. Moreover, the presence of ice reduces the rate at which warm ocean currents can be cooled by atmospheric exchange. Consequently, heat is retained in deeper layers, influencing global thermohaline circulation patterns. The insulating effect also protects Euro's ice habitats that support species, such as seals and penguins. If ice were denser, it would sink, eliminating this protective layer and drastically altering marine life. Thus, the molecular structure of water not only determines its density, but also shapes Earth's climate and ecosystems. Pause 0.8. When water freezes, its molecules arrange into a crystalline lattice that is less compact than liquid water. Hydrogen bonds form between oxygen atoms and hydrogen atoms of neighboring molecules, creating a repeating open framework. This framework keeps the molecules farther apart, increasing the average distance each molecule occupies in space. Because density is mass divided by volume, a larger volume for the same mass results in lower density. Ice therefore has a density of about 0.92 grams per cubic centimeter, while liquid water averages 1 gram per cubic centimeter. The difference is small but enough that ice floats on its own liquid counterpart. When you observe an iceberg or a frozen pond, the floating surface indicates this density inversion. This property protects aquatic life in winter by insulating the water below with a layer of less dense ice. If ice were denser than liquid water, bodies of water would freeze from the bottom up, disrupting ecosystems. The open lattice also explains why ice expands upon freezing, causing pipes to burst and glaciers to move slowly. In summary, hydrogen bonding creates an open structure that reduces density, allowing ice to float and expand. Remember, the key mechanism is the arrangement of water molecules into a less compact lattice during solidification. Pause 0.8. Ice floats because hydrogen bonds arrange water molecules into an open tetrahedral lattice, leaving spaces that lower overall density compared with liquid water. This structure not only explains Euro's trade as buoyancy, but also underpins many environmental processes.